Good morning, students. We are into online class. In the last offline class, I was on the chapter benzene and its derivatives. In this chapter, at the beginning, I started dividing organic compounds into aliphatic and aromatic compounds. Then I went through these examples of these structures. Then we were like trying to find out the structure of benzene. In the earlier days, they were not knowing the structure of benzene. They did know the molecular formula, but they didn't know the structural formula. Then I went on discussing how they got into benzene structure. Right, then we finally came to Kekule's structure and what Kekule said. Actually, Kekule said benzene is a cyclic planar structure of 6 carbons with alternating double and single bonds. And to each this carbon, hydrogens are attached. Then there were objections for Kekule structure. There were 2 objections. For one objection, first objection, Kekule answered that, and the second, for the second objection, we already know the answer on that. Kekule didn't answer that, but in a current position, we already know the answer for Kekule's the objections to Kekule's structure on the second one. Right. Now, in today's class, let's study on resonance and what is resonance, and let's also study molecular orbital picture of benzene. Resonance, it's a phenomena in which 2 or more structures can be written for a substance. There is one substance, and you can write that into 2 or more structures. So, and this substance, it is going to have the identical position of atoms. So this happens in benzene. Here are the structures. So benzene can be written in these 2 forms. You can see the position of a double bond. So here double bond is on here, but at the same position you have single bond here. The bonds are alternating, but these 2 structures are same, and when they are same and they are in high this resonance structure, you put them in a double arrow. These 2 structures can be written as one structure. So this structure is called as hybrid structure. This structure is called as a hybrid structure. So this resonance form, it occurs in a benzene. Right. Next, let's go for molecular orbital structure of benzene. I have discussed this structure in the previous class. These are principal shells in an atoms. So in an atom, at the center there will be nucleus and with the proton and neutron, and surrounding this nucleus you have the electrons, and these electrons are distributed in principal shells. So this is principal shell 1, like which is written here 1, and this is 2, this is 3, this is 4. Of course they are named like K, L, M, N, and see, this is second, this is third, this is fourth, it goes on like that. Now in each principal shell you have the subshells. What will the subshell will have? They will have these subshells like P, S and P. Here there is S subshell, here there is a P subshell. Again, each of these will have either 2, or the maximum number of electrons are 2 in the first one, 8 in the second one, 18 in the third one, and 32 in the fourth one. It goes on like that. Now each of these p subshells are again, they will have these orbitals. These are the orbitals, right? In case of p, you are going to have px, this orbital. You're going to have py, this orbital, and you're going to have pz, this orbital. And s orbital will be like this. These are dumbbell shaped orbitals. So you can put them together and it looks like this. And this is the shape of s orbital. This is s orbital, right? And if you put them together, it is going to have a picture like this. Right now, in carbon, there are you have 6 electrons, right? You have 6 electrons and they are distributed like this. 2 electron goes in the first principal level. So like this, 2 electron. So remaining is 4 electron out of 6 electron. 2 electron goes in the first principal shell, right? That is in 2s. Sorry, 1s here. The remaining is 4, and the remaining has to get distributed in 2 2s and 2p orbitals. So in the first one, of course, 2 is going to get filled, right? The first one has to be like 2, and the again, so 2 here in 1s, 2 in 2s, and 2 more electrons are remaining out of 6, right? Let's see how it will get distributed here. So out of those 2, what happens is 2 here, 2 here, and 2 remaining, right? 2 and 2 of this are here. Remaining 2, one will go to 2px, and the other one will go to 2py. So one will go here, 2px, right? One electron here, right? One electron here, and the other one will go here, 2py. And 2pz is empty. There is no electron for the 2pz. Now, whenever it is going to go form a bond, what will happen? They go to carbon. It goes to excited state. It goes to excited state. Now, one electron from 2s orbital, it gets transferred to 2pz. 2pz. Now you can see all of these 2s, 2px, 2py, and 2pz. They are going to have 1 electron each, right? Now further, what happens is during the formation of bond, hybridization will take place. Hybridization will take place. Hybridization will take place in case of a carbon here in benzene, 2ps, 2py, sorry, 2s, 2px, and 2py, they join together. These bonds, they join together. Which one? This one, and this one. 2px and 2py. They join together and they form that hybridization. They form the hybrid orbitals. These are dumbbell shaped orbitals. The resulting orbital will be like this. Now, 2s is forming the hybridization, 2px is forming hybridization, and 2py is forming the hybridization. The resulting will be like this. You will get 3 bonds. Here, all bonds are shown going through hybridization. But in case of benzene, only 3 of them, 3 orbitals, they are going to go for hybridization. Out of this shape, dumbbell shape, you are going to get this shape. One lobe is um, bigger, the other lobe is smaller. So this is the shape of hybridized carbon orbitals. Now if you put them together, it's going to be like this. It's going to be like this. If you put them together, it's going to be like this. So this is called sp2 orbital, because there is one s orbital and two p orbital involved. So one s orbital is from 2s orbital, right? And 2p orbitals are from 2px and 2pz. There is 2px and 2py, and there is a 2pz orbital remaining as it is. And the other thing is, all of these orbitals, they have the electrons. They have one electron in each, right? Even 2pz, it has got one electron in it. Now if you look at the carbon, if you put all these together, it should look like this. These are hybridized orbitals. They are sp2 orbitals, right? 2s and 2px, 2py, they join together and you will get this sp2 orbitals. And there will be one which is not in hybridization or unhybridized 2pz orbitals, and all of these will have one electron in each. Now you can see all those four electrons out of six, how they got arranged here. So this is a hybridized state of carbon. Now what happens? So what we will do is, this is of one carbon, so we have to take six carbon into consideration. Like benzene has got six carbon in it, right? So benzene has got six carbon. Now what we will do is, we will join this carbon to other five carbon. So how you can do is, suppose if I draw carbon here, another carbon here, and this is going to be like one sp2 orbital, right? I'm drawing another one here, sp2 orbital. I'm going to join another sp2 orbital here, right? And there is one more, this pz orbital. I'm going to draw that like this here. I'm going to draw this like this here, right? Now this is sp2. These two combined together, these two joined, right? This is sp2 bond, this is going to be sp2 bond. One electron of this and one electron of this, they join, right? They come together and there is going to be a bond formation here. Now this carbon again, it joins with another carbon here, another carbon here. So there is going to be sp2 orbital here. So like this, it is going to form bond, and this pz is going to form, or pz is going to have the electron as it is. Okay, it is not going to combine with any other atom. Now we have one more sp2 orbital here, right? This sp2 orbital is going to form bond with hydrogen. Now, two of the sp2 orbital, they are forming bond with the carbon and one with the hydrogen, and p orbital, the pz orbital, unhybridized pz orbital, it is going to be as it is, which you can see in this picture. They are joined together here. You can see carbon-carbon bonding here. These are all sp. These are all sp2 orbital. These are all sp2 orbital, and one of these sp2 orbital, they combine with the s orbital of hydrogen. Hydrogen is having only one electron in it, and it is going to form bond here, and that bond is going to be s and sp2 orbital. And these bonds are sigma bonds. All these bonds are sigma bonds. sigma bonds, and these are covalent bonds happen because of the sharing of electron. These are all sigma bonds, right? So there are two types of sigma bonds. One is sp2 sigma bond because of the carbon and hydrogen, and there are sp2 orbital sigma bond because of carbon carbon bonding. Now, because of this, the cyclic structure is formed, right? Cyclic structure is formed, and this structure is planar. This structure is flat. It remains flat, and the bond between the CC and CH, it is going to be 120 degree. Then each of carbon, it is going to have one unhybridized orbital, like I explained it before. So each of the carbon is going to have this comes from sp uh, 2 2pz. Okay, it is going to coming from 2pz, and it is going to have one electron in each. What happens, these electrons, they are going to revolve on this plane, on this structure, on the above, and this electron also can go below, and below also they can form a ring. This is the ring of pi orbitals. When they combine together, so it is going to form the pi orbital. It is going to form the pi orbitals. These are the electron clouds. These are the electron clouds which you can see here. All six carbon electrons of 2pz, 2pz, they are going to form the cloud like this. They are going to form the cloud like this, both above and below the plane of carbon structure, right? And because of this, this benzene is very stable. It won't let any electron to come in, or it also does not it won't leave its electron. It is not ready to leave its electron. That's why benzene is very stable molecule. Benzene is very stable molecule, and it won't undergo addition reaction. It undergoes substitution reaction. Suppose there is a bond, and bond, suppose it is a bond of benzene. Suppose it's like this, and because of this cloud, it won't let these electrons taken in the reaction easily. It won't give away the electron directly. What it can do is it can share its electron with the, suppose there is chlorine here, it can share the electron with the chlorine, and it is not going to give directly the electron directly to chlorine. It can form a bond with chlorine by sharing with the chlorine. It is not going to give the electron directly, or it is not going to lose the electron directly. That's why substitution reaction takes place in the benzene structure, and so that it wants to maintain its that ring state. It wants to maintain in its ring state. That's why benzene ring is very stable. Alright, next is aromaticity. What is aromaticity? Any aromatic compound, they should be like cyclic, planar. They should be cyclic. It should be in a joined cyclic way, the atoms, and it should be planar. It should be in a plane. It should have pi bond, and these pi bond electrons are delocalized. Like I said, the electrons won't stay at one place. They revolve over the ring. They move from one atom to another atom in their orbital, and this will give the stability to the ring, right? And if you compare with the other geometric structures with the same set of atoms, like see here, it is here this is cyclic and this is acyclic. This is not aromatic because it is not cyclic. It is not cyclic. So the structure should be a cyclic, right? And it should have this conjugated double bond, or conjugated conjugated in the sense, suppose carbon goes like this, it should have the sigma bond, um, sigma and pi bond alternating with the single bond, sigma bond. Sigma bond is double bond, this single bond, again double bond. So these structures are called conjugated, and that type of nature is there in the, will be there in the aromatic compounds. The aromaticity, it signifies the physical and chemical properties of the compounds. It determines aromaticity. It determines the, the property of the compounds, both the physical as well as chemical behavior of the compound, like how it reacts or how it looks, whether it's a liquid or solid form. So all this will be determined, depending on the aromaticity of the compound. Then there are requirements of aromatic in the aromatic compounds, like for the aromaticity there are four rules or four structural criteria it needs to be fulfilled to be aromatic. The first rule is it must be, the molecule must be cyclic. We know the benzene is cyclic in nature, right? The molecule must be cyclic. The second rule is it should be planar. It should be in a plane, or it should be a flat structure. It should be a flat structure. So benzene is a flat structure. Here, because pz orbitals, like they are aligned, they come together and they are bonded one to each other. This structure is planar, with the pi orbitals which are d localized, or pi electrons which are delocalized because of pz orbitals. Right, the third rule is atom must be conjugated, like I already said. It should have alternating double bond and single bond. In here it is not alternating, so it should have alternating single bond and double bond. Here that exists because of the unhybridized p orbital electrons. The fourth rule is a Huckel rule. It should fulfill the Huckel rule. Now, what is Huckel rule? Huckel rule is, it says any compound, Huckel rule, it says any compound to be aromatic, it should have 4n plus 2 electrons, where n is, any number like 0, 0, 1, 2, or, any number. If you replace this n with any number, whatever the resulting number it comes, if that many number of electrons are there in the structure, and then we can say that compound is aromatic. For example, you put 0 here, 4 into 0 is going to be 0, and the resulting is 2 electrons. Any compound, if it has got 2 electron, with other rules, it should fulfill the other rules, like it should be cyclic, it should be planar, it should have conjugated double bonds. And apart from that, if it fulfills this Huckel rule, if it has got 2 electrons, then it is going to be an aromatic compound. Let's put this n as 1. Let's see what will happen, like what it is calculated here. N equals 1. If we put n equals to 1, so that is going to be 4 into 1, that is 4, plus 2, that is 6. So total is 6. We are going to get 6 electrons. If any compound having 6 electrons, according to, with fulfilling all other previous rules, then it is going to be aromatic. And if we look at the benzene, we already know there are 6 2pz orbitals which have got 1 electron each. So benzene has got 6 electrons, and benzene is going to fulfill the Huckel rule. So benzene is an aromatic compound. So like this, if any compound has got 2, 6 or 10, 14, 18 pi electrons in the orbitals, they are going to be aromatic. Right, students. So this is about aromaticity and the molecular orbital structure of benzene. We also discussed about resonance. That's all for today. Let me know if you have any questions. Thank you very much.